2D material for transistor, memristor, synaptic, and live stimulated devices. I will give you one slide to introduce you Changchun University. Changchun University was founded in 1987, and currently we have the staff around 600, and student number is around 7,000. And our location is very nearby the international airport for Taiwan, Taoyuan. And we are the #1 private university in Taiwan, and our founder is the chair of Formosa Plastic Groups. And our industry contribute for 12% Taiwan's GNP. So now I will give you the introduction for my talk. I give you 3 quiz. The first one is what is the zero band gap material, especially for 2D material? Or what is a zero band gap, especially for graphene? And for 2D material, as you know, that's all the carrier just transport from the 2D dimension. So how to prepare for the dielectrics to have the good coupling to the material, that's also the important issues. And the third quiz is for the charge scattering due to the 2D material. So all the carriers are just transport on the 2D dimension will be a strong effect by the interface. So we call it charge scattering. So I give you the 3 answers or 3 aspects for my today's talk. One is for applications, and the second one is an all-powerful 2 is for fluorine or nitrogen doping. Due to the fluorine or nitrogen doping, it's very possible to have to open the band gap, especially for graphene. Or if we want to prepare for 2D dielectrics, fluorination or nitridation doping for 2D materials also are good options. And the third one is how to improve the charge scattering for 2D materials. One option or one solution is for the dipole compensation approach. So today, I want to share with you for the almost 10 years work. The first one, as I show you, is the doping and etching by plasma ambient. As you know, 2D material that's very sensitive for the environment. I mean, very sensitive to the process environment. So how to control the good doping and etching environment is very important. Our approach is using the plasma techniques. So we will introduce you later for details, but I just give you an abstract in this slide. And for the first figure here, that's for the plasma doping. We just using the plasma ambient with a filter. The filter is then silicone material, and it's transparent, but we just coating with carbon, with metal to just prevent the UV irradiation to 2D materials. And we also try to using these spatial techniques for doping, including fluorine and nitrogen, to perform the insulator or semiconductor. A semiconductor from graphene itself to a little bit opening of the band gap. And after we just prepare the spatial techniques for doping and etching, we try to scale up to 4-inch wafers. So in our lab, in our university, we can just have a scale up process for the 2D materials, especially for CVD. Even though it is a small grain size, but it's very possible for the future applications. So we just prepare 2D dielectrics. I will introduce you later, and we call it the fluorographene. If we just have the strong fluorine doping on graphene itself, the graphene will transfer to fluorographene. And eventually, we just using the fluorographene to prepare the high mobility transistors and the possible applications. So I introduce you for 3 quiz. The first one is zero band gap. For graphene is a zero band gap material. So how to just opening the band gap? There are a lot of researchers try to open the graphene band gap, including for the chemical approach. So for the chemical solution process, a lot of method it was introduced here, including the substrate-induced band gap opening or substitutional doping, etc. And our approach is just using the plasma dopings. So I introduced you earlier. We just using the filter try to filter the UV irradiations because we want to just perform the fluorine doping. So we just introduce CF4 plasma, CF4 gas. And during the plasma, UV irradiation will damage the 2D material very much. So that's why we're using the filter here. And we just check the UV irradiation will be much reduced. Almost 95% of the UV irradiation will be reduced. So under the good environment, we can prepare the 2D dielectrics. What are the possible candidates for 2D dielectrics? A lot of candidates, but it cannot equipped performed with a high electrical characteristics, including silicon dioxide, aluminum oxide, hydrogen dioxide, boron nitride, silicon nitride, and graphene oxide. But actually, the breakdown electric field cannot achieve to up to 10 megavolt per centimeter. So I will introduce you for the fluorination of the graphene. We call it the fluorographene. It's due to want to prepare the 2D dielectrics. So also from the literature, some researchers, they just find a good 2D dielectrics, we call it the fluorographene. The band gap can up to 2.9 electron volt, but it's unstable due to it's also the chemical process by the immersion of the graphene into the chemical solutions. But in our group, we just using the CF4 plasma, so try to open the band gap. How about the band gap opening? So I shall show you here. We're using the CF4 plasma using the timing from 1 minute up to 20 minutes. Due to the UV irradiation will be much reduced. So our graphene material can sustain in the CF4 plasma up to 20 minutes. The band gap can be opening from 0 band gap to 2.5 electron volt. So if we can have the good facility to prepare the 2D dielectrics and to prepare for the fluorine doping, and for example, another doping is a nitrogen doping. I will introduce you later. So we are so lucky to just perform the transistor of the graphene transistor for the mobility can up to almost 900 centimeters square per volt second. So after the third quiz introduction, I will just introduce you how about the mobility improvement by prevent the charge scattering. The charge scattering will just damage the charge transport on the 2D materials. So one of the charge scattering prevention will be just prepared by suspending graphene. It's empty with a void, just prevent the charge scattering. But our approach is just try to prepare for the fluorographene. It's graphene here. If we just prepare fluorographene underneath the graphene or with the partially fluorination or free fluorination, here is the fluorination for graphene top side and bottom side. So if we just using the spatial preparation of the dielectrics, then the charge scattering can just fully prevention by the dipole compensations. As you know, the dipole will be the charge scattering source for the graphene carriers in the graphene transport. So we will try to prepare the 2D dielectrics fluorographene just on top of graphene or underneath graphene. So if we just have a capping layer of the 2D dielectrics, just like sandwich. So graphene top with fluorographene or underneath with fluorographene, then we can just have the high performance transistors, graphene transistors. Here, I just introduce you for the mobility cam up to almost 3,000 centimeters square per volt second. So, and how about for another application from transistor base to the transistor base memory? So here I will move to the second applications for the memory as application. For memory applications, I will introduce you for the non-volatile memories. One of the non-volatile memories, we call it the flash memories. And another one I will introduce you as random RAM, random access RAM. So that's a resistor type. We call it RAM. So first, I will introduce you for the flash memory. For flash memory, that's a transistor with the floating gate structures. The floating gate structure can be continuum film, or it can be also prepared by the nano crystal structures. So here I will introduce you for the nano crystal structure. It's due to if we have some leakage paths for the floating gate, the fully connected floating gate, you will be high leakage if we just have a small leaky path. But for the nanocrystal, all the floating gate is isolated. It's due to the nanocrystal structures. So the leaky path can be standalone, be very independent. So it can be with the highly retention performance for the memories. So here we just using the graphene based. How to prepare for the graphene based as the floating gate? We just using for the eventually we have the structure like the figure G. We have the top gate is the metal gate, but we have the embedded of floating graphene with the nano crystal graphene structure. It's due to you have the graphene transfer first, and then we have the gold. And after the high temperature rapid thermal-anneal, the gold will be nuclearized, and then it will be performed with the nanodisc. And the nanodisc can be just as the hard mask to pattern the graphene as the nanodisc. So we can prepare the GND, means graphene nanodisc structures, as our floating gate, a nano crystal floating gate structures. So as our check, we just checked by SEM for how about the scale. The scale is just around for some tens nanometers. So we can perform the high performance with the very, very less charge loss. For 10% charge loss can sustain to 10 years. So for the flash memories, we just try to check how about the resistor type memory applications. So we also using our fluorographene as the dielectrics to perform the two terminal. The top terminal is to perform my STM chip, and the back button electrode is just by our graphene. So it's a two terminal, looks like resistor, but we have the interfacial layer with our fluorographene, and we just check for the leakage current, it can be conducted even though it is dielectrics, but with a high electric field, the dielectric will be a leaked current due to the FN tunneling or direct tunneling. So the turn current can perform as a different step, and it looks like stepwise, but it's also like analog and digitalized. So it's very possible for the possible memory applications. That's why I want to share with you for the synaptic devices. The synaptic devices that are very similar to our neuron. So as a neuron device that is with some stimulate, and then the carrier or the electron or holes, the ions will transport through the synaptic pathway to next cells. So we just simulate for the transistor type, and the transistor type is different to our RM. Our RM is 2-terminal, but now I will introduce you for the transistor type memristors with 3-terminal. For the 3-terminal, we have source and the drain and the gate. And how about the channel? Our channel is graphene, but we have the dielectrics with fluorographene and aluminum oxide. So as we just check our materials by the TM, and then we checked our electrical performance, and we can check our electrical performance, and it can be turned on and turned off with the programming from the low resistance to high, or from high resistance to turn on with the low resistance, and switching back. Then the resistor will be terminate, and then it will be looks like resistors. So with the low current and the turn on with high current, and the sweep off as a sweep to the negative voltage, then it will be from the high turn on current to the turn off current levels. So there's an on off. So it's also like a memory, but it's looks like analog applications. We call it like synaptic performance. So how about the synaptic performance? I will show you another example later. So the last part I want to share with you is for the light stimulated synaptic devices. Earlier I introduced you for the electrical stimulated synaptic devices for the fluorographene based transistor. Due to some stress, the electrical current can be from the low current to the high current, and from the sweeping to voltage, positive voltage, and the sweeping back to negative voltage. You will turn on and turn off. And how about for the light stimulated synaptic devices? I introduce you another material. Is the Bi oxide synonized. So we call it simplified by box Bi2O2Se. And what's the difference for the electrical and optical synaptic? So for electrical synaptic, it's introduced high energy, but for the optical electronic synaptic, we just with no need for interconnections, because as you know, light is very easy to perform. So we have a spatial structures here. We just have a combined two materials. One is for graphene, another is for the BIOSE. So that's box materials, and the different materials, they have a different absorption for the light, for the different wavelengths of the light. And due to the different light stimulations, then the electrical performance will be also changed. So we just have the different combination of the light introduced, the light stimulations, and the response for the different materials will have the different combinations. So we have different wavelengths, different light intensity to introduce the different, they post the effect of the light-induced currents. So under different light, we can just perform and with the long-term potentiation or long-term depression of the different materials. So we just have a different light input for the red wavelengths and for the green wavelengths. And our modulation light input is then for the UV irradiations. So under different combinations, we can just perform for the digital logic gate functions. So due to time is limited, I just give you a quick conclusion for my talk. For graphene has demonstrated the possible materials for the high band gap and with the good semiconductor performance. And then we just perform for the high mobility transistors and for the memory applications. For the box material Bi2O2Se combined with graphene materials, we can perform for the photodetector and the photo-induced opticals, synaptic devices as well. And thanks for your attention for my talk. And I want to have a special acknowledgement to my collaborators just shown in the slide here. Thank you very much. Thanks for your attention. And